Hi there. In part 1 I was trying to repair this Sony amplifier with the channel not working. This amp is based on a long obsolete Sanyo STK465 hybrid IC which needs to be replaced but is no longer available. 2 attempts to replace it with cloned STK465s failed. One clone working but producing unacceptable distortions and the other not working at all. I first considered getting some off-the-shelf amplifier module, of which there are dozens available, and replace this whole section. The problem with that is that the tone controls are an integral part of this circuit, so one would either have to live without tone controls or make the new amp module work with the sliders of the original circuit, or fix the new amp module's tone controls to the front panel. All not very attractive solutions. So how about just replacing the STK465 with a different chip? To get an idea of what is needed, here's the inside of one of these STK465 hybrid ICs. It contains basically 2 op-amps, each with Darlington output stages. I apologize for the poor quality of this historic datasheet, but we won't dwell long on it, just to explain why this thing has so many pins. First thing, there are 2 positive power rails. Pin 9 feeds the rail of the positive Darlington stages, and pin 8 is the positive rail for the op-amps. Secondly, the positive and negative part of each output stage is not internally connected to drive one output pin, but instead runs to pins 6 and 7 for the left channel and 10 and 11 for the right channel. In the application schematic of the datasheet, it is clear that one should connect the Darlington positive and negative stages externally with a low ohm resistor, like here, and then they drive the speaker. Also, the positive supply rail for the op-amps is simply connected via a 100 ohm resistor to the one for the Darlingtons, and there is an extra filter cap for this rail. I suppose all this was needed because the necessary components didn't fit into the envelope of the IC. Here is again the relevant part of the schematic of the Sony amp. You will now recognize some of the stuff from the STK465 datasheet. Here is the extra positive supply for the op-amps with a filter cap, and here are the resistors to connect the split output lines from the Darlingtons. All these complications are specific for the STK465 and not needed for a generic solution, and it's likely that everything else can stay. This may be a bit of a gamble, as the resistors and capacitors for the tone controls in the feedback loop were of course specifically dimensioned to work well with the STK465. As a replacement, I decided on an LM1876. This small package has actually just 1 pin less than the STK465, but they are in this staggered 2-row configuration. The STK465 is enormous in comparison. So yes, it has a lot of pins, but I won't use quite a number. The chip has a standby mode to reduce power consumption, but there is no way to make that work in this amp. For the same reason, I won't use mute either. Thankfully, just leaving the pins not connected disables both of these functions. It is true that this chip is less powerful than the STK465, about 20 watts versus 30 watts, but I think it's plenty loud enough. The big problem with this chip is the supply voltage limit of max, and this is truly max, 64 volts. What they mean is of course plus minus 32 volts. You may remember from part 1 that the amp's power supply is designed for plus minus 35 volts, but I measured plus minus 33 and a bit. If you park supply voltage issues for a moment and accept to forget standby and mute, the actual application couldn't be simpler. The TI datasheet contains detailed guidance in designing the power supply and the dimensioning of the components of this circuit. I'm not going into the details here, but put a link to the datasheet in the description of this video. The caps marked as CS are recommended to avoid slow oscillations or motorboating if the amp is some distance away from the smoothing caps. The feedback network of RF, RI and CI selects the gain and frequency bandwidth. My plan is to simply try connecting this chip to the existing feedback network originally designed for the STK465 and hope that it works for this chip too. For the problem of the supply voltage, I considered 3 options. Starting from the top, I can use regulators to get rid of the excess part of the voltage. I need, of course, positive and negative regulators, and I do not want switching regulators because of their noise. This limits the choice, and it would be basically the usual LM317 and LM337 solution. These are rated for 1.5 amps, which is a little low for the LM1876, but since we may have to get rid of, say, 6 volts only, that reduces the thermal load, so they may handle a bit more current before limiting. Still, we would need to find a good way of mounting the regulators and their heat sinks. On the plus side, this solution provides a stable and ripple-free supply to the LM1876, which can be adjusted to not exceed specs, regardless of mains fluctuations. The second possibility is to use strings of rectifier diodes. Each diode in forward direction will drop a little bit of voltage, so with a number in series we can get rid of a few volts. For example, the 1N5401 is rated for 3 amps max current and has a maximum forward voltage drop of 1.2 volts. Unfortunately, the voltage drop is depending on current, and with no music playing and hence very little current, the drop is only 0.6 volts or maybe even a bit less. So we need probably 8 or 10 in series on both the positive and negative side to be safe, even with maximum mains voltage. When the music gets louder and the current increases, the voltage drop increases too, just when the amp needs all it can get. So, while inexpensive, this is not ideal. Cooling and mounting is still an issue, but a lot easier than regulators, as the heat dissipation is spread over all diodes, so no special heatsink would be needed. The third possibility is to attack the root of the problem, reducing the high supply voltage at the source, namely the transformer. Lucky people living in 115 volt countries may do that simply by setting the voltage selector to 230 volts, and now you have 2 times 12 volts instead of 2 times 24. Unfortunately, for 230 volt countries you will have to replace the transformer, an expensive proposition unless you happen to have a suitable one lying around. With 12 volt or 15 volts AC, this reduces the supply voltage so much that while the LM1876 is definitely in specs, the maximum achievable output power is now reduced. Another issue is that the reduced supply may cause problems in other parts of the amp. Now, with all this in front of you, which solution do you think I selected? Yes, I selected the last solution because I did happen to have a spare 2 times 15 volts transformer in the parts bin. So let's disconnect the wire wrapped output from the existing transformer, which uses a center tap configuration. Once disconnected, it allows investigating how the rest of the circuit will tolerate a lower supply. Just to confirm, the idle AC output of the old transformer at the current mains voltage is about 53 volts over the whole windings, or 2 times 26.5 volts with center tap. That means it's very likely a 2 times 24 volts transformer. A quick look at the way the power supply works in this amp. Let's start with the schematic on the left. AC from the transformer comes in, gets rectified and smoothed, and provides the plus minus 35 volts for the STK465. In addition, it gets through 1 or 2 resistors on each rail, depending on the model. I have the E model, so it's 2 resistors in series. These feed a conventional stabilization circuit consisting of a pass transistor and a Z diode to create a plus minus 15 volts for the rest of the circuit. Finally, there is an additional single diode rectifier and smoothing cap that takes the AC to provide a 24 volts for the relay. The intention of these resistors I mentioned are to drop some of the voltage before it gets into the stabilization circuit, so the pass transistors don't have to convert so much excess into heat. That's possible because the load and therefore the current draw on the 15 volt circuits is pretty constant. So with that current, the designers calculated resistor values that drop just enough but not more to make the stabilization work even when the mains voltage is at its lowest limit. Notice that R415 in the positive connection to the regulator is lower in ohms than R416 in the negative connection. That's because the positive 15 volt supply is running the front panel LEDs and therefore the current is higher. So far so good. Now have a look at the PCB layout on the right. It turns out that the schematic isn't quite correct. For the E model, R415 and R416 are not implemented and instead replaced by wire bridges, just like for the US and Canadian models. So there's only one resistor per voltage rail, R409 for the positive and R412 for the negative connection. The values are still different. R409 is 100 ohms and R412 150 ohms. To see if these resistor values are a problem, I replaced the AC feed temporarily with 2 times 21 volts DC from a bench power supply, resulting in about minus 20.3 volts after passing through the rectifier, and of course the same on the positive side. Now on the negative rail, R412 reduces that to about minus 14.3 volts, and on the positive side, R409 leaves 16 volts. Those values, especially the negative one, are too low for the regulators to still work properly. And indeed, instead of about minus 15 volts, we have just minus 13.6. And while the positive regulator is nearly there with plus 14.5, this is still too low. Conclusion: yes, with a reduced AC feed from a 15 volts transformer, these resistors have to be substantially lower. In fact, in the end, I simply replaced them with wire bridges. This means the same voltage driving the new chip will now be the input to the regulator. With a 15 volts transformer and high mains voltage, this will be in the order of maximum 25 volts, which is about 10 volts lower than before, and a test with a bench power supply confirmed this is totally fine for the pass transistors. If you happen to have an 18 volts transformer, you should put in 20 ohm resistors instead of wire bridges. The datasheet of the transformer. It's a toroidal one, which is anyway better than the original. It is smaller, more efficient and causes less interference. It has 2 primary 115 volts windings, which I can connect to the existing voltage selector, allowing 115 volts with both windings in parallel or 230 volts with both in series. The original transformer offered a third option of 220 volts, which I can't implement with this one. The 2 secondary outputs will be connected in the middle to provide a single winding with a center tap. The model I have is the TheHWcave type, which does 2.67 amps on each secondary, good enough for the LM1876. The regulation value for this model is stated at 11%. What this means is that the output is 15 volts and 2.67 amps, but with no load the output will be 11% higher. 11% of 15 volts is 1.65 volts, so I should see 16.65 volts AC. But that is a mains voltage of 230 volts. Normally my mains voltage is at least 235 volts and often even higher. So I should see a bit over 17 volts AC. This regulation swing between idle and full load is something all transformers have. Since the LM1876 has a maximum allowed voltage limit, the transformer choice must assume the worst case, that is the amp is idle and mains voltage is at its maximum. In the UK this means 230 volts minus 6% plus 10%. In other words, mains voltage if up to 253 volts are normal. That would put the AC voltage to above 18 volts and the resulting DC voltage to just under 26 volts, still well below the maximum of 32 volts. I removed the old transformer and mounted the new one, which is easy since there's only one hole to be drilled for the center bolt to hold the new transformer. With the new transformer and basically no current draw, the AC voltage is indeed more than 17 volts. Testing the smooth DC output against ground shows minus 23 volts for the negative rail and plus 23 volts for the positive one. These values are as expected with this transformer, but means that the amp's output power will be a bit less than the maximum possible. And testing the 15 volt regulator outputs, we have minus 14.9 volts for the negative rail and nearly the same for the more loaded positive rail. That is all fine. Now on to the LM1876. This is the schematic of how to fit the LM1876 to the pinout of the STK465. It looks more complicated than it is because all I did is connecting the inverting and non-inverting inputs and the outputs, of course, to the equivalent pins of the STK465. Based on the recommendation in the TI datasheet, I did add additional electrolytic caps for VCC and VEE and to each of these a 0.1 microfarad cap in parallel. I put this on a little Perf board, but because of the staggered pins of the LM1876 I had to use one that supports this raster of 1.27 millimeters. This board implements exactly the schematic except for the pinout on the connector. It turns out that an STK465 compatible pinout is difficult to achieve on this Perf board. The LM1876 on the PCB is oriented in such a way that its rear can be mounted to the heatsink, which also holds the PCB itself. It goes where the STK465 was, but instead of upside down, it will go the right way up, and I drilled a center mounting hole in the heatsink for it. Some heatsink compound and it's ready for mounting. Here it is mounted, just hovering over the components on the motherboard, but of course not touching anything. I used a connector that pushes over the pin headers and wired that connector to the original PCB that connected the STK465. As you can see, some of these wires crisscross. This is because of the different pinouts of my PCB and the STK465. I hooked up speakers and an MP3 player with some YouTube audio library titles and powered it on. No smoke? It actually worked. I was curious how the tone controls worked with the LM1876 instead of the STK465, and they do just fine. But the scope revealed something else that I could hear. There was a constant and very noticeable mains hum on the output, which you see on the scope as an overlay on the 1 kHz waveform. My first action was to check the two smoothing caps, branded Nichicon 4700 microfarad 42 volts. What could be wrong? To my total surprise, they both turned out bad. Maybe not totally bad, but with only 2700 microfarad, this one has lost half of its capacity. And the other one with 2658 microfarad is the same. Well, if they came from the same batch, as it's likely, they both will have the same flaw and failed in the same way. I replaced the caps with new ones that have indeed 4700 microfarad each, but the mains hum did not go away. My theory is that this hum is picked up by my wiring to the new PCB. Neither these wires nor the tracks on the Perf board are shielded in any way, and originally the connection to the STK465 was way shorter. How to fix this problem? I could think of only one way: develop a proper PCB that connects much more directly. With the schematic you saw earlier, I designed this little board, which is more compact and it allows me to match the pinout of the original chip. I also left as much of a ground plane as possible to improve shielding. One thing to note is that different from the Perf board, on this PCB the LM1876 will be upside down, just like the original STK465. This is so the connection board fits easier and means that the pin headers are now on the backside of the PCB. Once I was happy with my design, I sent it off to PCBWay, who are sponsoring this video. Collecting the design files in the right format for production is very easy because there's a PCBWay plugin for KiCad, making this a one-click operation. A web page opens with your board loaded and the options set to sensible defaults. An image of the front and rear gives some confidence that PCBWay was able to interpret the design correctly. There are plenty of parameters which may be confusing, but each parameter has a help, and as I said, most of them will be set to sensible values already, as in this case. I left all the values like PCB material, thickness, spacing and hole size, solder mask color as they were. As you can see, the cost for 5 of those PCBs is just $5, which is great for us hobbyists with not a lot of money, but a willingness to wait a bit longer, because the shipping costs can easily add $25 or more if you want your boards fast. In my case, I selected global standard shipping, 6 to 8 business days, for just $3.69 to the UK. When you push the button to move it to the shopping cart, an additional verification process is started where PCBWay experts look at your design and your chosen parameters, and when they approve it, you can proceed to pay. If they find an issue, they notify you so you can fix the problem first. This is a good safety net, especially if you don't design PCBs every other day. For this design, the approval process took just a few minutes and no issue was found. For some reason my previously selected shipping method was not automatically pre-populated in the checkout, but not to worry, I can still choose my preferred, much more affordable shipping method. And now all you need to do is push place order and pay, of course. And 2 weeks later a rather large box, giving the size of my PCBs, arrived, nicely sealed in shrink wrap. Inside a sealed bag, hopefully containing my 5 boards. And yes, there they are, just as I designed them. I'm particularly interested if I did the unusual footprint for the LM1876 correctly, so the chip will fit. The rest of the components are very standard. I removed the chip from the Perf board, which wasn't the easiest desoldering job, and it fitted perfectly into the new board. I also moved the electrolytic caps to the new board, but I didn't bother with the 0.1 microfarad caps and used new ones instead. And here's the new PCB mounted on the heatsink. As I said, the LM1876 and all other components are now upside down, but the pin header is the right way up for the connection board. It fits easily and all I have to do is solder it in. By the way, on the right you see the 2 new large 4700 microfarad smoothing caps I mentioned earlier. Power it on. No smoke, which is a good sign. Speakers are connected and an MP3 player with YouTube audio library tunes. It's working and no hum, finally. Remember the hum visible on the scope when testing the tone controls? No more hum visible now, and the tone controls work just as before. Interestingly, the rectangular waveform looks most square if the treble control is slightly in the negative instead of neutral. I did a frequency plot with all controls in the neutral position. The -3 dB frequency range is from 30 Hz to 30 kHz, which isn't bad, but it's not as flat as I would have liked it. A bump of about 1 dB. Well, that's what I get for reusing a feedback network designed for another chip 30 years earlier. Out of curiosity, I repeated the plots with the tone controls in their extremes, always with the neutral plot as reference in blue. On the left we have the bass slider, yellow when fully set and red at its weakest setting. On the right is the same for the treble control. Yellow is fully engaged and red the weakest setting. The last plot is for the loudness button. In summary, the controls work just fine and I think the effects are maybe a bit extreme, but nobody forces you to push the sliders all the way. As I already noticed when checking the tone controls with a rectangular wave on the scope, for a mostly flat frequency plot it's advantageous to move the treble slider slightly into the negative. With that setting, the plot between 80 Hz and 10 kHz can be pretty much evened out. I could end this long video here, but there is a tiny bit more. These days a major source of music is coming via Bluetooth and these modules are so cheap, why not adding one? This one isn't as straightforward as you might think. It needs 5 volts and when I experimentally fed it through a 5 volt regulator from the plus 15 volts in the amp, I got a lot of interference on the audio, no matter what additional filtering I added. This is a common problem with Bluetooth modules and their spiky power draw. It worked fine when powered from mains via an old USB charger, of which I have tons lying about, so why not use it? In this test setup, the mains connection to the USB charger is done very ropey using croc clips. An old earphone cable is plugged in the audio out and the other end is tacked into the audio input. Satisfied that this would work without interference, I made it slightly safer and presentable. I glued a small plastic box on the charger side to the mains connection. This serves 2 purposes. I added a metal plate that has threads for M3 bolts to fix the whole thing in the amp, and when the lid of the box is closed, the mains prongs of the charger are safe from being touched. On the underside of the amp are the 2 bolts that hold the Bluetooth add-on, and I decided to replace the old unshielded earphone cable with a properly shielded cable soldered into the module. The other end is still using the same solution to tack the wires into the aux input. The power is connected to one of the unused wire wrap terminals of the rear power outlets. Still need to do the heat shrinking though. The heat shrinking done, and I also tidied the AC connection from the transformer to the rectifier. I was curious what the max output power now actually is, so I connected this little rig consisting of 4 8-ohm resistors, 2 for each channel. They can be connected by themselves for 8 ohm or in parallel for 4 ohms or in series for 16 ohms. Here they are connected for 4 ohms and a scope and multimeter are attached to one channel. Feeding a test tone of 1 kHz, I crank up the volume until the amplifier starts clipping and then reduce it until it no longer clips. A rather crude method, but good enough for a ballpark figure. The voltage is about 8.22 volts AC RMS. With 4 ohms, this means a current of 2.05 amps and a true continuous power of 16.9 watts. Still plenty loud enough. Doing the same with the load resistors wired for 8 ohm results in about 10.7 volts AC RMS, meaning a current of 1.34 amps and therefore a true continuous power of 14.3 watts. I just realized that I have not demonstrated the Bluetooth interface, so here we go. While that's going on, time to sum up. All in all, for sure, just the time spent makes this a rather expensive repair, but in the end it was very satisfying giving this old amp a new lease of life. I'm planning to add the PCB design as a free download into the PCBWay shared project library. Look for the link in the description of this video. If you like my videos, don't forget to like and subscribe, and maybe becoming a Patreon. That would really help this channel. The link's in the description. Thanks for watching.